Thank you, Manuel. Hello, everyone. My name is Pablo Moreno Escolástico. I'm working under the guidance of Rodrigo Castellanos, Andrea Chini, and Marco Raga. And, well, even though today we'll be talking about propulsion, I would reshape the title of this presentation to more something like Propulsion System Optimization for Sustainable Aviation. Why? Okay. First, let's start with the motivation. As my colleagues have introduced before, also especially Joao with the more innovative architectures and that projects, especially under the umbrella of clean aviation here in Europe, these projects are pushing towards new aircraft architecture for more sustainable aviation and net zero emissions, which are pushing indeed to have new propulsion architectures that are more efficiently or with different arrangements than the one that we know nowadays. This brings us to the need for new design methodologies, new design tools, which is indeed what we are trying to do in ODE4ERA, that is the project I'm working in, where we are trying to build an open digital environment for hybrid electric regional architecture. And all of this brings us to the question we want to answer, that is, how can we design the next generation of sustainable aviation propulsion systems? For this, first we need to go to the state of the art. And here I would like to remark three main takes. First is that propulsion system has become a more multidisciplinary problem, like the one that our colleague Raul published in 2024, where not only a multidisciplinary problem, but also a highly integrated problem within the airframe architecture. Secondly, multidisciplinary design optimization, MDO, tools like GEMSEO that Joao mentioned, or OpenMDAO, is becoming the standard for this kind of analysis. But, however, current design tools and methodologies are based on either sequential sizing or fixed correlation coefficient. This poses the gap that are two, indeed. One is the lack of physics-based multidisciplinary sizing tools to have different performances along different conditions, and that sequential sizing design fails to capture multidisciplinary problems and the interactions between those subsystems and disciplines. For this, to address this, the methodology we have chosen to follow is to build, the objective is to build a preliminary design tool which is physics-based, to capture all the physics behind all the components, so all the system, but also perform simultaneous optimization to capture and to be able to understand all the interactions between all the systems and the components that are being there, which are not few. Then we want the design tool to be modular and incremental for allowed for the most architecture possible, the different components, etc. So everyone can design their desired architecture with a few changes. And an important novelty of these tools would be that they will not only do mechanical sizing or mass estimation of the components, but we do both at the same time. However, having a hybrid electric power plant is a very big system and very complicated dynamics, so we decided to split it in three main parts that are very differentiable. One is the electric branch, and the other one would be the internal combustion engine, more traditional one, and the other the propulsive element, that is the propeller. For this, we decided to start first with the electrical branch, where we had to select an architecture for the hydrogen electric powertrain. For this, we need to choose a power generation system, which is the fuel cell, which can convert hydrogen and air into water and electricity, which will power an electric motor for giving mechanical torque to the propeller to generate thrust. And we also need to alleviate all those electrical loads that are transformed into heat. So we also included a thermal management system, which is composed by an air inlet duct and a ducted heat exchanger. Not only that, but for the sake of completeness and modularity, we also included another power source, that is the battery, enabling either battery or fuel cell power or both of them. Here is where the hybridization factor comes to play, that you can find many different definitions of the hybridization factor in the literature. However, here we are defining it as the fuel cell power out of the total power of the system, meaning that if we have a hybridization factor of 0.7, the fuel cell is providing the 70% of the power and the battery the other 30%. Once we have decided our architecture, we can build our multidisciplinary optimization framework, which is based on gradient-based optimization. Especially, for the moment, we have used SLSQP algorithm that allows us to do gradient-based optimization using also constraints on manufacturing side, on operative side. They can be whatever we need. Once we have this, our framework, we can perform an analysis or optimization. In this case, we decided to select a use case of a small commuter, a Dornier DO228, which is an aircraft capable of transporting up to 20 people, powered by these two turboprop engines of a maximum power of about 600 kilowatt each one. First, for this analysis, what we did was first to size the powertrain for a fixed condition, which is a takeoff condition, the maximum power we have. And then once the geometry is fixed and we have our desired powertrain, we perform a second optimization, which is the admission level. In this case, we are optimizing the hybridization factor achieved at each mission segment, takeoff, climb, cruise, and descent. So we have the most optimal flight profile that you can see there in the right, with at the takeoff around 40% of battery power, and it decreasing until in cruise we have only fuel cell, which is more light. At the end of the mission, as you can see in the hydrogen mass panel, for a 1 hour flight, we consume about 13 kilograms of hydrogen. And to finish, I would like to pose the next challenges I will be facing. That I said that we divided the work into 3 main blocks. However, they are indeed very complex, each one of them. The electrical propulsion is almost done. So once it's finished, we can move to the other 2. First, the propulsive element, the propeller, which our objective is to expand the current bend capabilities, the blade element momentum theory model capabilities that we have, including structural considerations to understand and study how the deformation and deflection affect the propeller performance, to include also our acoustic, as Joao commented before. This is an important problem that is not always well studied for these devices, and performing also optimization of the propeller in terms of geometry and number of blades, and if possible, do some control of pitch or RPM control, which depends on the architecture you are choosing. On the other hand, we have the internal combustion engine that is more traditional, less innovative, let's say. However, this problem is very known at thermodynamic level, but not that studied at aircraft integration or hybrid electric architectures. For this, we will perform a more detailed turbomachinery design, enabling also the usage of different fuels like jet A1, kerosene, sustainable aviation fuel, or hydrogen for combustion, and allowing different engines like turbofan, turboprop, or the novel architecture profan, which is the one we have here in the middle, enabling more modularity and more incremental work. These are the contributions I've made during this year. A couple of conferences I will be attending this year. We also sent an abstract for the EASN conference, where we are having a dedicated session of Out4ERA and other dissemination activities and courses. And before finishing, I would like to give special thanks to Marco, the master, that even though he's not my official supervisor, he's always giving a lot of help, giving a lot of advices, no matter when, no matter what, he's always willing to contribute and to help. And that would be all. Thank you.